Our next topic in solution chapter is colligative properties. So those properties which depend on the number of particles of the solute, those properties are known as colligative properties, and these are of four types. First one is relative lowering in vapor pressure. Second colligative property is elevation in boiling point. Third is depression in freezing point. And fourth is osmotic pressure. So we'll do these properties one by one. So first we are starting with the relative lowering in vapor pressure. And the derivation of this relative lowering in vapor pressure we have already done in the Raoult's law. The formula was P naught minus Ps upon P naught equal to X2. This we have derived, where P naught is the pressure of the vapor pressure of the pure solvent, Ps is the vapor pressure of the solution, and X2 is the mole fraction of the solute. So what is P naught minus Ps? P naught minus Ps we have done is the lowering in vapor pressure. So in the solvent, when non-volatile solute is added, then there is lowering in vapor pressure. And how much lowering is there? P naught minus Ps. The pressure of the pure component minus that of the solution. So lowering in vapor pressure. And what is P naught minus Ps? When we divide it with the P naught, that becomes the comparison we can have, and that is called relative lowering in vapor pressure. So relative lowering in vapor pressure is equal to the mole fraction of the solute. So this already we have derived, and the B part of this colligative property is we have to conclude that this is a colligative property. To conclude that relative lowering in vapor pressure is a colligative property. From the formula itself, it is clear that since this relative lowering in vapor pressure depends on the mole fraction depends on the number of moles of the solute, hence this is a colligative property. So from the expression only, it is clear that relative lowering in vapor pressure depends upon the number of moles of the solute and is independent of its nature, hence it is a colligative property. And third part of the colligative property is we can determine the molecular mass of solute with the help of any colligative property. So when we are doing these colligative properties, first we'll do the derivation of this thing, we'll understand the meaning of that colligative property. Then second part is we have to conclude that it is a colligative property, and third part is with the help of any colligative property we can measure the molecular mass of a solute. So determination of molecular mass of solute with the help of a colligative property, that is relative lowering in vapor pressure. Now the formula we know is P naught minus Ps upon P naught, which is equal to X2. X2 further we can write equal to N2 upon N1 plus N2. What is N2? Number of moles, that is equal to mass upon the molar mass. Again, mass of this component upon its molar mass, and number of moles N2 is W2 upon M2. Hence, with the help of this formula, we can calculate the molar mass of the solutes, because in the formula there is a molar mass of solute. Hence, from this formula, M2, that is molecular mass of solute, can be calculated. So this is our first colligative property. Now moving on to the second colligative property, that is elevation in boiling point. Elevation means increase in the boiling point. Now what is boiling point first of all? Boiling point is a temperature. Which temperature? At which vapor pressure becomes equal to atmospheric pressure. The temperature at which both these pressures will be equal, that temperature is known as boiling point. Now we have a graph here. One side we are taking a temperature and other side we have a vapor pressure. Now we plot it for a solvent and for a solution. Now when we take a pure solvent, goes with increase in temperature. When temperature we are increasing, its vapor pressure will keep on increasing. And when we take a solution, remember here a solution is when solute is non-volatile. When to the solvent a non-volatile solute is added, we have done its vapor pressure decreases. So curve of the solution will be lower than that of the curve of the pure solvent. But even here for solution also, as the temperature will increase, its vapor pressure will increase. So this is the curve for the solvent, this is for the solution. And let's say at this point, this is the vapor pressure, that is atmospheric pressure. So at this point, this vapor pressure becomes equal to atmospheric pressure. So this is the temperature of solvent TB naught at which it will start boiling. So it's a boiling point of pure solvent, because at this temperature vapor pressure becomes equal to an atmospheric pressure. Similarly for solution, vapor pressure becomes equal to this atmospheric pressure at this temperature, that is TB. So this is the vapor pressure of solution TB and this is of solvent. So to solvent, when non-volatile solute is added, there is elevation in the boiling point. And how much elevation is there? That is TB minus TB naught is elevation in the boiling point, denoted by delta TB. Delta TB is TB minus TB naught. And what is delta TB? This is how much boiling point is increasing on adding a non-volatile solute to a solvent, elevation in boiling point. And we also know delta TB is proportional to molality of a solution. And to remove the sign of proportionality, we use a constant Kb. This constant is called molar elevation constant. Molar elevation constant, or also called abelioscopic constant. If molality of solution we take unity, then Kb is equal to delta Tb, and we can define molar elevation constant here, that molar elevation constant is equal to elevation in boiling point when molality of the solution is unity. So if molality is 1, then Kb is equal to delta Tb, and from here we can define it, that is molar elevation constant. This is equal to the elevation in boiling point when molality of solution is unity. So this is the first part of this colligative property, that we have explained what is elevation boiling point along with its formula. Now moving on to the second part here, that is we have to conclude that elevation in boiling point is a colligative property. Now since this depends on the molality, and molality is number of moles means particles, so we will say yes, elevation in boiling point is a colligative property. It is a colligative property because it depends upon the molality, and molality means number of moles of solute in 1 kg of solvent, hence it is a colligative property. And third part of colligative property is, with the help of this colligative property also we can determine the molecular mass of solute from elevation in boiling point. Since we know that delta TB is equal to KB into M, and KB is equal to KB into M, and molality is W2 upon M2 into 1000 upon W1. And this entire chapter, as already I told you, that one subscript we are using it for the solvent, for the solute, and 2 we are using it for the solute. Hence, molecular mass of solute, that is M2, can be calculated with the help of this colligative property, that is elevation in boiling point, because in the formula there is M2. So this is about the second colligative property, that is elevation in boiling point. Moving on to the third colligative property, that is depression in freezing point. Now what is freezing points? Freezing point, again, this is a temperature at which the solid and liquid states of the substance coexist. Same substance, but its solid and liquid states are coexisting. That temperature is known as its freezing point. So a solution freezes when its vapor pressure is equal to vapor pressure of pure solid solvent. A solution will freeze when its vapor pressure is equal to vapor pressure of pure solid solvent. Since we know that solution vapor pressure is always less than the pure solvent, so this means it would become equal, that this vapor pressure will become equal to solid solvent at a low temperature. As compared to solvent, the freezing point of the solution will come at a low temperature, and difference in the freezing point when we'll take of the pure solvent, that will denote by TF naught, and when we take of the solution, the difference that is denoted by TF, this difference is known as depression in freezing point. Like if we have a graph for this thing, from graph only we'll understand this point. Again, one side we have a temperature, one side we have a vapor pressure. We have done that the solvent vapor pressure is always more than that of the solution. So solution curve is here, like the elevation in boiling point we have done. This is solution and this is of a solvent. And remember, this is a liquid solvent. So now what we'll do is we lower down the temperature. When we lower down the temperature, what will happen? Vapor pressure will keep on decreasing. A time will come when from liquid it will change to which state? It will change to the solid state. So at this temperature, this is solid solvent. This is a temperature at which solid and liquid state of the solvent will coexist. That means at this temperature solvent will start freezing. So this is the freezing point of pure solvent. This TF naught, this temperature is the freezing point of solvent. Now solution also, when we will lower down the temperature, what will happen, this will also start, vapor pressure will start decreasing, and at this temperature you can say here it will start changing to which state? Solid state. So at this temperature it's solid and the liquid states, they coexist. Vapor pressure here we have done that of solution is always lower than that of the pure solvent. So if its vapor pressure is lower, that means its freezing point will also come at a low temperature. This is what we have explained here. The solution freezes when its vapor pressure becomes equal to vapor pressure of the pure solid solvent. Since vapor pressure is less than that of solvent, solution vapor pressure is always less than that of the solvent. That means its freezing point will also come at a low temperature as compared to that of the pure solvent. And this is denoted by TF. So as compared to the solvent, if you will take the solution, its freezing point is lower. How much lower is this? That is the difference of the freezing point of the pure solvent and that of the solution. This is TF naught minus TF. So we can write this as delta TF, which is equal to TF naught minus TF, and this is called depression in freezing point, and this is also proportional to the molality. And if proportionality, a constant Kf will come here. This constant is known as molar depression constant, or this is also known as cryoscopic constant. And we can define it. If molality of the solution is 1, then Kf will be equal to delta Tf. Now we can define this molar depression constant. This is equal to depression in freezing point when molality of the solution is unity. So molar depression constant, this is equal to the depression in freezing point when molality of the solution is unity. So this is the first part of this colligative property that we have explained. What is depression in freezing point? Now coming to the second part of this colligative property. In second part we always have that we have to conclude that this colligative property, that is depression in freezing point, is a colligative property. It is a colligative property. Colligative property means this is dependent on the number of particles. Now in the formula we have written delta TF is equal to KF into M. M is there. M means number of moles of solute in 1 kg of solvent. Since this depends on number of moles of solute, that means this depends on the number of particles of solute. Hence, it is a colligative property. So, depression in freezing point is a colligative property because it depends on molality. And molality means number of moles of solute. Hence, it is a colligative property. Now moving on to the third part of this colligative property, that with the help of this colligative property also we can calculate the molecular mass of solute from depression in freezing point. As in the formula we have delta TF is equal to KF into M, and then molality we know is equal to mass of solute upon its molar mass into 1000 upon mass of the solvent. So since in this formula there is M2, so with the help of this colligative property, from depression in freezing point, molecular mass of solute, that is M2, can be calculated. So this is about this colligative property that is called depression in freezing point. Now only one colligative property is left in this, that is osmotic pressure, that we'll do separately.